Okay, on to our second one. It's trig substitution. Um, why? So why trig substitutions? Because the trig identities are some of the most staple, tested and tried identities in math. They're from one of the oldest branches of math. They go all the way back to ancient Egyptians building the pyramids. Weren't they smart? So anytime you see an expression like this, guys, I want you to think trig identities. And what do we have here? We have an x squared plus an a squared. Yes, we have a lot of other stuff, and I have purposely chosen this integral to be able to solve by trig substitution. So let's work through it, and you'll see. So I have an x squared plus an a squared, and what gives me a plus sign? Tangent does. Tangent is a pretty cool dude. He's pretty positive. So when you see a plus sign, think tangent, and tangent squared plus 1, right? That's what we're going for. So I'm going to let my x equal what this tells me, which is a tangent theta. My a is 2, not 4. Remember, a is squared right there. So 2 tan theta, and then I'm going to take the derivative of both sides, and derivative x equals 2 is my constant. It's just going to come down. It's a constant of a function, so its derivative is not 0. I have to say, I have repeated that enough to remember. So I got this. So let's go take these guys to the good old theta world. And so what do we have here? We have 1 all over my x squared is, we define x to be 2, tan theta, so I have 4 tan squared theta because I have x there and I have x squared here, so I could just easily square everything. Same thing inside, I have 4 tan squared theta plus my a squared plus 4. And don't forget our d, because we still have to replace dx, right? So we have 2 secant squared theta d theta. So if you're following so far, let's simple this guy out. We have 4 tan theta. I think you can easily see that if I factor out a 4, I am left with tan squared theta plus 1, because if you multiply that back in, you get exactly what you started with. And I think you can now see that that is nothing but what I was looking for. So I have 4 times secant squared theta, because tan squared theta plus 1 is secant squared theta. And given that this is a multiplication and not a subtraction or addition, I can just go ahead and legally pull these guys from under that stinking radical sign. So what do I have here? I have a 2 in the denominator, I have a 2 right there. I have a secant here, I have 2 of them up there, and I could get rid of one of them. Then I have 1 over 10 squared theta times secant theta d theta. I'm going to bring my 1/4 out. And rather than writing this as 1 over tangent, you all know that tangent is sine over cosine, and they both are squared. So, and 1 over this, it's really just the inverse of that. So I could write down cosine squared theta over sine squared theta times, and secant is, if you remember your trig rainbow, is really just 1 over cosine. And this is going to make my life so much easier right now. I'm going to love it. Look, I have cosine here, and I have 2 of them right there. I can get rid of one of those, and I only have now a 1 cosine left and 1 sine squared left to deal with. But I did this ahead of time to save some time on this. So I went and solved this by u substitution. I let my u equal to sine theta. So let's write that down right here. Let's get this, guys. Let's just make sure we remember these are separate. So what do I have here? I have, if I let my u equal sine, which is right down here, my sine is squared, so I have to square u. And I get cosine d theta back, and if I divide both sides by cosine, I'm going to be left with a cosine on top here, remember that, and I'm left with a cosine du over cosine right here, right? These two guys cancel. And what do I have here? I have 1 over u squared, which is the same as saying I have u to the negative 2 power. And guys, don't forget your 1/4. It is a bad habit I got. And then du. And this is where we always like to get, because this is probably the easiest thing to solve as far as integrals go. The power rule is really helpful. That is nothing but u to the power of negative 1. Negative 2 plus 1 is negative 1, and I have negative 1 in the bottom. That means it makes my entire expression negative. So I have negative 1 over 4. And then u to the power of negative 1 is the same as 1 over u. But what is my u? My u is sine theta, so I'm just going to write that right here instead, because I'm hoping you followed through with me so far. And then I could put a plus sign and we're done. Just kidding. We're not even there yet. So we're almost there though. We're almost there. So let me take out this u and I can u substitution. I'm not taking out u, just the u substitution, and get us back to the x world. So we defined our x to be 2 times tan theta. If I divide both sides by a 2, I'm left with an x over 2 tan theta. And so I've gone ahead and drawn a right triangle. So tangent is opposite over adjacent. And then my hypotenuse is this guy squared plus this guy squared, which will give me my hypotenuse squared, but I don't need the squared version of it. I need it under the radical sign. So that is my hypotenuse. And what is sine? Sine is opposite over hypotenuse. So let's rewrite this guy. Equals to negative 1 over 4. And then I said opposite, right, over hypotenuse, so I have x on top, and my hypotenuse, which is x squared plus 4 on the bottom. I can rewrite this to something a little prettier, which would equal to negative, remember, they have that whole inverse situation going on here, 4 right down there. So this guy will go on top, square root of x squared plus 4 all over x. Now I can go ahead and do my plus c, because plus c, guys, it comes when